Hi, everybody, and welcome to Math 4426-5526, Complex Analysis. My name's Dr. Rossi, and I'll be teaching the course. This is the first day of our course in Term 5 of Summer 2020. You've probably seen the syllabus on Canvas, and if you have, you've probably seen what the text is and also my email address. If you do not yet have a text and you're having trouble getting a text, please email me. I may have an easy solution, okay? If you don't already have a text, email me and I think maybe I can get you fixed up with a text easily, okay? Now, let's dispense with the formalities. This is a new topic for all of us. And so there are going to be some definitions and some examples that we're going to have right at the beginning of the course. And we could say it's a necessary evil, but it's also a good thing. We're not going to assume very much as far as our background goes. We do need to know how to integrate and differentiate as far as calculus goes. But other than that, we don't need to know much. Let's define this. The square root of -1 that we denote by a lowercase I. Almost always when we see a lowercase I in mathematics, lowercase I represents square root of -1. Now, if we have any real number b, and we compute the product of b and I, so this is b times I, this number bi is called an imaginary number. An imaginary number, it's the product of a real number times I, the square root of -1. And don't let this terminology fool you. Imaginary number, it's a figure of speech. It's been around for hundreds of years, probably since the time when mathematicians really did think that this was an imaginary number. It doesn't exist. The fact is, the number bi has a great deal of significance in mathematics and engineering, particularly electrical engineering. It is not really an imaginary number, but maybe several hundred years ago, mathematicians thought that it was. Before I give the next definition, let me draw attention to this capital R. This is a capital R with two vertical lines going down on the left-hand side. This is our symbol for the set of real numbers. So anytime we see this in a course, this represents the set of real numbers. So here's our definition. Given any two real numbers a and b, the number z equals a plus bi is called a complex number. So this complex number z, what is it? It's the sum of the real number a plus the imaginary number b times I. Anytime we compute the sum of a real number and an imaginary number, we get a complex number. And there's some terminology that we should use for later on in the course. This is more than just useless definitions. So this is going to have significance as we get on into the course. A, this real number that we use to form the complex number z, A is called the real part of z, and it's denoted this way, capital R-E parentheses z, the real part of z. The coefficient of I in a complex number, in this case b, is called the imaginary part of z, and is denoted capital I-M parentheses z. This is not useless terminology. Probably by about the time we get into the middle of the course, we're going to have a lot of cause to use these two things. Now, look at this C right here, this capital C. It's a capital C, and then I have a vertical line right there. This is our notation for the set of complex numbers, capital C for complex. So the set of complex numbers is the set of A plus BI for any real numbers A and B. So it's the set of all numbers that can be formed by adding a real number plus an imaginary number. Now, before I hit the pause button, we should probably look at some examples just for clarification. Is that a complex number? Well, it's the sum of a real number, 3, plus an imaginary 4 times I, so, yep, it's a complex number. Now, what about this? What about this? Z equals 3.6 minus 5.4i. Is that a complex number? Well, it's the sum of a real number, 3.6, plus an imaginary number, negative 5.4 times I. So yes, that is a complex number. The real and imaginary parts don't have to be whole numbers. And this does not have to be a plus sign here. It could be a negative sign. Okay. What about that? Is that a real number? What do you think? The answer is yes. Now, how do we justify this? Z equals 3 is a real number. How can we justify this? Because the number Z equals 3 can be written as the sum of a real number plus the imaginary number 0 times I. So it is a real number plus an imaginary number. So the bottom line here, what we want to remember is that every real number is also an imaginary number. No. Every real number is also a complex number. Every real number is a complex number. The converse is not true. Not all complex numbers are real numbers, but every real number is a complex number. Now, you probably know what I'm going to do next. What about that? Is this a complex number? You know the answer, don't you? It is a complex number. And our reasoning is z equals 2I can be written as the real number 0 plus the imaginary number 2I. Real number plus imaginary number is complex number. And I just looked at what I had written above and realized I may have said what I meant, but I didn't mean what I said, or vice versa. What did I really mean to put here? What should go here? Okay. Now, for those of you who are about to have a heart attack, please forgive me. Yes, the point to this particular example is that any real number is also a complex number. Z equals 3 is a complex number because we can write Z equals 3 as the sum of the real number Z plus the imaginary number 0 times I. 3 is the sum of a real number plus an imaginary number, so it is a complex number. And I'm going to break for a second, and I'll be right back. Okay, brand new blackboard. Any complex number, z equals x plus yi, can be represented as a point in the xy plane. And x and y have the conventional connotations. In other words, x is the displacement of the point from the y-axis, and y is the displacement of the point from the x-axis. And in complex variables, y always represents the imaginary axis. Okay. The modulus of a complex number. We'll give the definition and then we'll give the geometric significance. The modulus of the complex number z equals x plus yi is denoted this way. It looks like absolute value of z. And the modulus of z is given this way. Square root of the real part squared plus the imaginary part squared. That's how we do it. And let's look at the graphical interpretation. The modulus of z represents the distance from the origin to this point z, or vice versa. The modulus is the distance of the point z from the origin. And let's make some sense out of that. Here's the origin, here's the point z, and the modulus of z represents this distance. It's the distance from the origin to the point z. And let's see why it is that the modulus of z equals square root of x squared plus y squared. Well, remember what y is. Y is the vertical displacement of the point from the x-axis, or y is the distance of the point from the x-axis. So, this distance is y right here. And you know what? Just to make it make more sense visually, I'm going to draw it this way. So y is the distance of the point from the x-axis, and x is the distance of the point from the y-axis. So guess what? We have a right triangle here. The base of the right triangle has length x. The height of the right triangle is y. So by Pythagorean's theorem, the hypotenuse, which is the modulus of z, the modulus of z, is just the square of the horizontal leg plus the square of the vertical leg, square root. So that's how we get the modulus z. And z is the distance of a complex number from the origin. Okay, let's do some examples. Our instructions are graph z and compute the modulus of z. So the real part, which is x, is 6. So we mark out 6 units on the x-axis. And the imaginary part is 4. We mark out 4 parts on the y-axis. And there's the real number 6 plus 4i. Now, as far as the modulus goes, The modulus of z is the square root of the real part squared plus the imaginary part squared. So it is that 36 plus 16, 52. Okay. And if we were to draw the modulus, z, this distance is square root of 52, a little bit more than 7 units. So that's example number 1, where A let's go to B. Complex number -3 minus 2i. The real part, which we mark on the x-axis, is -3. And the imaginary part, which we mark on the y-axis, is -2. So here's our real number, here's our complex number z, -3 minus 2i. Now we have to compute the modulus of z. And that's the square root of the real part squared, -3 squared, plus the imaginary part squared. So let's see, 9 plus 4 is 13, square root of 13. So here's our modulus z. And it's a distance of square root of 13, or a little bit more than 3 units from the origin. And last but certainly not least, let's do this one. Z equals 4 minus 3i. Our real part is 4, so we mark out 4 units on the x-axis. Our imaginary part is -3, so we mark out -3 units on the y-axis. And there we have it. Z equals 4 minus 3i. Yeah, I guess that works. And now we compute the modulus of z. And to get that, we take the real part, 4, and square it. And the imaginary part, -3, and square that. And we get 4, 16 plus 9 is 25. Okay. So our modulus is 5. So the point z in this case is exactly 5 units from the origin. Ta-da! And maybe I should make a remark. Did that make it in? Oh, it did. Good. Now, how do I want to word this? Notice that the way that we've been graphing complex numbers is exactly the same that we graphed the vector z with x and y components. We could very well say that this thing is vector z is the vector with an x component of 4 and a y component of -3. So the way we graphed vectors with two components in linear algebra is exactly the same way that we graph complex numbers in the xy plane. We've had linear algebra, we've graphed vectors before. Graphing complex numbers is exactly the same. So we have something to compare all of this to. Okay, arithmetic operations involving complex numbers. We'll start with the easy stuff first. Addition and subtraction. Complex numbers z1 equals x1 plus y1 times I, and z2 equals x2 plus y2 times I are added by, first, adding the real parts, and then second, adding the imaginary parts. Now let's see how this works. We have the complex numbers z1 and z2. So right here, this is our z1, and this is our z2. And the directions say we add the real parts. So x1 plus x2. There we have it, the sum of the real parts. Then we add the imaginary parts, y1 plus y2. And here we have it, y1 plus y2, sum of the imaginary parts, times I. This is how we add two complex numbers. Now, subtraction is done analogously. Yes, subtraction is done analogously. Complex number is x1 plus y1i, and z2 equals x2 plus y2i are subtracted. First, we subtract the real parts, and then we subtract the imaginary parts. So here in our example, we're subtracting z2 from z1. So here's z2, here's z1, and we subtract the real part of z2, which is x2, from the real part of z1, which is x1. So real part of z1 minus real part of z2, the difference of the real parts. And then we do the same thing with the imaginary parts. Imaginary part of z1, imaginary part of z1 minus the imaginary part of z2. y1 minus y2. y1 minus y2. And have we seen something kind of like this before? I think we have, and in just a second I'm going to show you where we've seen this before. Didn't have quite the same appearance, but we've seen this before. Okay, you're probably saying to yourselves, I've seen this before, and you're absolutely right, you have. Adding and subtracting vectors, we've done that before, is essentially the same thing as adding and subtracting complex numbers. So, complex numbers z1 equals x1, y1i, and z2 equals x2 minus, no. Let me change that. Let's make that a plus. Yeah, I like that much better. Complex numbers z1 equals x1 plus y1i, and z2 equals x2 plus y2i are added and subtracted component-wise. Remember that from linear algebra? We add and subtract vectors component-wise. So complex numbers are added and subtracted component-wise, the same way that vectors are added and subtracted. That we have the vectors z1 and z2, and we're adding them. So we take the first components, x1 and x2, and add them. And we take the second components, y1 and y2, and we add them. That's how we add vectors. It's also exactly the same way that we add complex numbers. And how do we subtract vectors? We take the first component of the first and subtract the first component of the second, x1 minus x2. And we take the first component, we take the second component of the first vector and subtract the second component of the second vector, y1 minus y2. This is the difference of the two vectors. We subtract complex numbers exactly the same way. So let's look at a couple of examples. Let's look at a couple of examples. We add complex numbers component-wise, real plus real, imaginary plus imaginary. So let's do the reals. The real of the first, the real part of the first plus the real part of the second. So that's 6 plus 8. And the imaginary part of the first plus the imaginary part of the second, 3 plus 4, times I. So we have what? 14 plus 7i. Okay, let's do subtraction. According to the directions that we had, we subtract the real part of the second from the real part of the first. So we have real part of the first minus real part of the second. Real part of the first minus real part of the second. Plus imaginary part of the first minus imaginary part of the second times I. And that gives us 2, no it doesn't, it gives us negative 2 minus I. Ta-da! Now, multiplication. We multiply complex numbers pretty much the same way that we multiply two binomials. Let's see, most of us, I guess, when we were in high school, we learned the, quote, FOIL method. First, outer, inner, last. Hey, it works. So let's do that. What's the first thing that we do? We take the first and we compute that product, AC. And then let's see, FO, okay, so now we take the outer and that's A times DI, so ADI. First, outer, inner, okay, so next we take the inner, and that's BI times C. And then lastly, we take the last two. So the last of the first times the last of the second. BI times DI. Now, we're going to have to simplify this. Let's see, AC, AD, these two terms have a common factor of I, so I'm going to factor the I out of these two terms. And I'm going to get AD plus BC times I. Cool. And here we have two factors of I, so I'm going to write that as B D I squared. And we can still simplify. AC, I like that. And I have AD plus BC times I like that. I squared. I is the square root of -1. So if I square I get -1. So that's plus BD times -1. Okay. Well, this is a real number. B times D times -1. Real number times real number times real number is a real number. So I think it's time now for me to group all of my reals together and all of my imaginaries together. I have real AC and I have real negative BD. So that's AC minus BD. And the imaginary part I have all nicely packaged already. So plus AD plus BC times I. Well, you know what? That was a lot of work. Maybe we can do a little bit better. Maybe we can do a little bit better. And maybe I can do a little bit better. I'll just move this down slightly. And what did we get? We got AC minus BD, that's the real part. And the imaginary part, that was AD plus BC times I. We have the product of the real parts, and it's a real number. And now we also have product of the imaginary parts, and that's a real number. Because we have I times I, that's not imaginary, that's real. I times I is -1. So we have real number B, real number D, times I squared, which is -1. That's real number times real number times real number. BI times DI is a real number. And we get imaginary part times imaginary part times -1. So if we multiply two complex numbers together, the real part of that product is going to be the product of the real parts minus the product of the imaginary parts. Everything else having to do with the product of two complex numbers is going to be imaginary. Let's see. The inner and the outer. If we take the product of the outer, we have a real times an imaginary. That's imaginary. AD times I. And if we take the inner, it's going to be an imaginary times a real, which is imaginary. BC times I. So that's what we're looking at when we multiply two complex numbers together. The real part of the product is the product of the real parts, A times C, minus the product of the imaginary parts, BI DI. And see, when we multiply I times I, we get -1, and that's what gives us this minus sign here. Everything else is imaginary. We do the product of the outers, A times DI, that's real number times imaginary number, is an imaginary number, AD times I. The product of the inners, imaginary number times real number is imaginary. So that gives us BC times I. This ought to make it fairly easy for us to remember how to multiply two complex numbers together. Now let's look at a couple of examples, okay? Okay, real part first. We take the product of the two real parts, that's 2 times 6, minus the product of the two imaginary parts, so that's 3 and -4. Now let's see, the imaginary part. We have the product of the outers, 2 times -4, plus the product of the inners, 3 times 6, so let's see, 12 minus a -12. And we have -8 plus 18i. There we go. Now let's do another one. First, we'll get the real part, and we take the product of the two real parts, 8 times 4, and now plus, nope, that's not right, is it? Product of the real parts, and then what do? Minus the product of the imaginary parts, because we're going to have an I times an I gives us -1. Okay. So product of the real parts minus product of the imaginary parts, and that's -5 times a +3. Okay, there's the real part of our product. Now we do the imaginary part. We do the outers, 8 times 3, plus the product of the inners, -5 times 4, times I. And let's see what we get. 32 minus 15 minus a -15 is +15. Okay, there's the real part. And the imaginary part, we have 24 plus a -20 is 4. So 47, let me see, I ran out of fingers here, I miscalculated. 8 times 3, 24, yeah, how does that sound? So 32 plus 15 is 47, and we have 24 minus 20 is 4i. So there's our answer. Okay, an important concept in complex numbers is something called the complex conjugate. Here's how we define it. Given the complex number z, real number a plus imaginary bi, the complex conjugate of z, or just the conjugate of z, is denoted as z with a bar over it, and it's given by z conjugate equals a minus bi. So the conjugate of a plus bi is a minus bi. So what do you think the conjugate of a minus bi would be? Well, the conjugate of a minus bi is a plus bi. So I guess we figured out that in order to compute the conjugate of a complex number, we just change the sign of the imaginary term. So if this is a plus and we want the conjugate, we just make it minus. If this is a minus and we want the conjugate, we just make it a plus. It's that simple. Now, let's do a couple of examples. Okay. In each case, we just want to compute the complex conjugate of each number. So, z conjugate 2 minus 3i. We just changed the sign of the imaginary part. Next, we want the conjugate of negative 3 minus 4i. And all we do is we change the sign of the imaginary part. So this is the only sign that we're going to change. The complex conjugate is negative 3 plus 4i. And then finally this guy. We want the conjugate of 5 minus 4i. So we change the sign of the imaginary part. 5 plus 4i. Well, that was easy enough. For those of you that still have a recollection of Calculus 1, where we had a limit of the form 0 over 0 and we needed to cancel out a common factor in numerator and denominator, we may remember that the trick was to take the numerator, which was square root of something minus something else, and we multiply that numerator and the denominator by what we called the radical conjugate. And we just took the sign of what was in between the two terms and changed it from positive to negative or negative to positive. We're going to do very much the same thing here, and this is a very special kind of product. When we multiplied a radical pair by its radical conjugate, we got an expression that didn't have any radicals in it. And that's important. Radicals, when we have them, especially the square root of the sum or difference of two or more terms, it's hard to work with algebraically. So if we can get rid of that radical, we like that because it frees us up to simplify things and combine things algebraically. A similar thing is true of complex numbers, and when we multiply a complex number by its conjugate. Let's see what happens when we do that. We have a complex number, a plus bi, and we have its conjugate, which is a minus bi. What happens if we multiply these two things together? Z times z conjugate. So we have a plus bi times a minus bi and we'll get the real part of the product, we take the real part of the first times the real part of the second, which is a squared, minus the real part, the imaginary part of the first times the imaginary part of the second. So that's b times negative b. And now we do the complex part. And to do the complex part, we take the outers, a times negative b, plus the product of the inners, b times a, times I. And what does this turn out to be? A squared minus a negative b squared, so that's a squared plus b squared. That's the real part. And then we have negative ab plus ab, which is 0. Son of a gun. This is very important. It turns out to be very significant and very useful. That's what we get when we multiply a complex number by its conjugate. That we get essentially the real part squared plus the imaginary part squared. Now this is essentially true. The product of a complex number and its conjugate is always a real number. And it's always going to be positive unless, I know how I can doctor this up. I hate for people to call me a liar. The product of a non-zero complex number and its conjugate is always a positive real number. It's always a squared plus b squared. And that is going to be more important than you can imagine. And believe it or not, in this lecture, we're going to find out one of the reasons why that is so important. See, the only time that the product of a complex number and its conjugate is 0 is when that complex number is 0. So if we have a non-zero complex number and we multiply by its conjugate, we get a positive real number. That is going to be immensely important. And the most important part about this is not the positive part. The most important part about this is that it's real. We take two complex numbers, complex number times its conjugate, multiply them together, and the i's disappear. There's no imaginary term. Just like if we take a radical pair and multiply it by its radical conjugate, the radicals disappear. This is going to be immensely important. And let's see, how soon are we going to see this? Well, I guess we're going to do a couple of examples first. And then we're going to see why this is important. Okay, first example. Here's our complex number, 4 plus 3i. And we're going to multiply it by its conjugate. So we have z, and here's z conjugate. Just change the sign of the imaginary term. So here's z, here's z conjugate. And what we get is the real part squared plus the imaginary part squared. See, let me do it this way. The real part squared plus the imaginary part squared Okay, z equals -5 minus 12i. So we multiply z by z conjugate, we get -5 minus 12i, and -5 plus 12i, but we change the sign of the imaginary term. So here's our z, and here's our z conjugate. So what do we get? We get the real part squared plus the imaginary part squared and there's the product of z and z conjugate. Now, why is this important? I can't tell you just yet, but very soon we'll see. How do we divide this complex number by this complex number? I have absolutely no idea how to do this. I don't know. So what I'm going to do, I'm going to hit the chicken switch, and I'm going to solve a problem that I know I can do. Yep, I hit the chicken switch. I don't know how to divide one complex number by another complex number. I chickened out. So what I'm going to do instead is I'm going to solve a problem that I know I can do. I'm going to divide a complex number by a real number. That wasn't exactly what I wanted to do now, but I'm going to do it because I know I can do it. And I'd rather do something that I know I can do and succeed rather than do something I know I can't do and fail. So I'm going to do what I can do right now. I'm going to divide a complex number by a real number. I'm just going to put this in the numerator and I'm going to put the divisor C in the denominator, like this. Well, look what I have. I have two terms in the numerator over a single term in the denominator, so I can break this up into two separate terms. So I take the first term and put it over the denominator. And I take the second term and put it over the denominator. Okay, it was a cowardly thing to do, but I said, I don't really know how to divide one complex number by another complex number. So what I'll do is I'll divide a complex number by a real number just because I know I can do it. And here's the way I did it. Now, in doing this, my eyes have been opened to a strategy for dividing one complex number by another complex number. So here's the quotient of complex numbers. The thing that I can't do, the thing that I'm scared to death to try because I'm just sure I can't do it. I'm going to take this thing, the quotient of two complex numbers, the thing that I don't know how to compute, and somehow I'm going to rewrite it as an expression that is the quotient of a complex number and a real number, because I figured out up here that I know how to do that. So I'm going to take something that I don't know how to do, dividing one complex number by another complex number. And I'm going to convert that into an expression that I do know how to work with, namely the quotient of a complex number and a real number. Is this easier said than done? I hope not. I want to take this thing and convert it into the quotient of a complex number on top and a real number on the bottom. How am I going to do that? How am I going to get rid of this complex number on the bottom and replace it with a real number instead? Do you have an idea? How do I take a complex number and somehow operate on it and turn it into a real number? Well, remember just a couple of minutes ago we were multiplying a complex number by its conjugate? And we found out that the product of a complex number and its conjugate is a positive real number. So that's all I have to do. I have to take this piece of junk in the bottom, this complex number in the denominator, and multiply it by its own conjugate to turn the denominator into a real number. And I know how to divide complex numbers by a real number. So that's my strategy. I'm going to take this complex number and I'm going to multiply the denominator by its own conjugate. Hey, I can't do that. That's illegal. You're right, it is. So to atone for that sin, I just multiply the numerator by the same value. And this is perfectly legal. This is not 0, so its conjugate is not 0. So I'm not dividing by 0 here. And any non-zero number divided by itself is just equal to 1. All I'm doing is multiplying the original expression by 1 in a clever disguise, but I'm doing it in such a way that the denominator is going to be a real number. Okay. So let me do the easy part first. Like I said, I'm in a cowardly mood today. I'm going to do the stuff I can do easily first. The product of a complex number and its conjugate. We take the first term and square it, plus the second term and square it. The bottom is a real number. Now I got to multiply out the top. So we'll do the real part first. Product of the reals minus product of the reals, product of, what are these? The last. So product of the reals, product of the imaginaries, that's it. Product of the reals, product of the imaginaries. So I'm going to get B times negative D. So that's it. Product of the reals minus product of the imaginaries. That gives me my real part. Plus the outers, A times negative D, plus the product of the inners, B times C, all of that times I. So let's see, I get AC plus BD plus negative AD plus BC times I, all of that over C squared plus D squared. I have two terms over a single denominator, so I'm going to write the first term over the denominator, AC plus BD over C squared plus D squared, plus the second term, and I don't like to put a negative term first, so I'll say BC minus AD. Over that same denominator times I. That's the quotient. Okay. By being cowardly, I found a good way to do this where I didn't directly have to divide one complex number by another complex number. I simplified the problem by multiplying top and bottom by the conjugate of the bottom. And that made the bottom a real number. And that transformed my problem from the quotient of two complex numbers, which I can't do, into the quotient of a complex number and a real number, which I can do easily. That's the way that us cowards divide one complex number by another. That's also the way that everybody else in math divides one complex number by another. This is the standard way of dividing one complex number by another. So, we had this worked out with A's and B's and C's and D's. Let's do it again with real numbers. Oh, by the way, I told you that the product of a complex number and its conjugate was going to be important, didn't I? This is one of the reasons why. Okay, first example. Our procedure is to convert this into an expression where the denominator is a real number. And we do that by taking the original expression and multiplying top and bottom by the conjugate of the bottom. The bottom, we're going to get the real part squared, and we're going to get the imaginary part squared. And on top, what do we get for the real part? We get the product of the real parts, which is 6. We get the product of the imaginary parts, which is 24, but we subtract that, don't we? We have the product of the reals minus the product of the imaginary, so that's minus 24. So that's our real part. Now the imaginary part. We have the product of the outers, 3 times 4 is 12, plus the product of the inners, 6 times 2 is 12, all of that times I. And now we simplify. Let's see, negative 18 plus 24i, all over, let's see, 4 plus 16 is 20. So I get 18 over 20. No, I don't. I get negative 18 over 20 plus 24 over 20i. And just reducing, that's negative 9/10 plus, let's see, common factor of 4. So 6/5 I. And that's the quotient. Wow, this was not that hard after all. Maybe I was afraid for nothing. Let's do another one. 4 minus 8i. Okay, we do this the same way. Our goal is to transform this into a quotient where the denominator is a real number. So we take the original expression and we multiply top and bottom by the conjugate of the denominator. So that's going to be 3 minus 3i. 3 minus 3i. Okay, excellent. And on the bottom, we have the product of the reals squared and the product of, we have the real part squared, 3 squared. We have the imaginary part squared, 3 squared. Okay, that sounds better. On top, for our real part, we have the product of the reals. 4 times 3 is 12. 4 times 3, 12. Minus the product of the imaginaries. Negative 8 times negative 3. And now our imaginary part. We have the product of the outers, 4 times negative 3, plus the product of the inners, negative 8 times 3, all of that times I. And let's see, this is positive 24 minus is negative 24. 12 minus 24 is negative 12. And what about over here? Negative 12 minus 24 is negative 36. I. All over, let's see, 9 plus 9 is 18. So negative 12 over, well, I'll write it out. Negative 12 over 18 minus 36 over 18 times I. So that's negative 2/3 minus 2i. So that is my answer. Now, one more example for division of complex numbers. And this is sort of a special case. Let's just look at it. We want to take that expression and just write it as a complex number. Now remember something. Every real number is also a complex number. So this is the quotient of two complex numbers. We'll treat this the same way we treat every other quotient of complex numbers. We'll multiply top and bottom by the conjugate of the denominator so that we'll change the denominator into a real number. So, conjugate of the denominator, just change the sign of the imaginary part. 4 minus 5i. 4 minus 5i. Beautiful. And on top we get 4 minus 5i. On the bottom we get the real part squared. No. On the bottom we get the real part squared. Yeah. 4 squared. Plus the imaginary part squared. So what is that? 41 maybe? 16 plus 25, I think so. There. So we took the reciprocal of a complex number and just wrote it in standard complex form, a plus bi. Excellent, excellent, excellent. Okay, observations about the modulus of z. The modulus of z is the square root of z times its conjugate. Or we could say the square of the modulus is equal to z times z conjugate. And here's how we get that. Z times z conjugate is equal to a plus bi times a minus bi. And remember what we get. We get the real part squared, and we get the imaginary part squared. Now, if we were to take this and take the square root and then square it, we get the same thing back. So a squared plus b squared is the square root of a squared plus b squared squared. But what is the square root of a squared plus b squared? Isn't that the modulus of z? So z times z conjugate is the modulus of z squared. Or the modulus of z is the square root of z times its conjugate. Let's see, what else would we like to note here? Oh yeah. Typically, the properties that hold for absolute values also hold for the modulus. So the modulus of z1 times z2 is going to be the modulus of z1 times the modulus of z2. And there's a similar or analogous result for the quotient, or the modulus of a quotient. The modulus of z1 over z2 is equal to the modulus of z1 over the modulus of z2. And then finally, z1 plus z2 modulus. Now just look at this thing down here, and what do you think we're going to do with it? The modulus essentially is analogous to the absolute value. So if you guessed that it's going to be less than or equal to the modulus of z1 plus the modulus of z2, you guessed right. So those are some important observations and properties about the modulus of z. They're worth remembering. Also, I'd like to give you a few algebraic properties of complex numbers, and I'm going to try to make these as general and as few as possible. How do I want to say this? Observations, okay. Addition and multiplication, they're commutative, they're associative. So the distributive laws work. Multiplication distributes over addition and subtraction, so we get z1, z2 plus let's make that a z3. z1, z2 plus z1, z3. and Z1 times Z2 minus Z3, Z1, Z2 minus Z1, Z3. Okay, that's enough for the first lecture. I'm going to be sending you a homework assignment by email. And again, if you have issues with getting a text, if you don't have a text yet, or if you can't get the text, just email me because I think I can help out in that regard, okay? And before we go, let me just say, welcome to complex analysis. It's going to be a great summer.